Hello everyone, I am Akash Panda. I am going to present our work on nuKSM, that is NUMA-aware memory deduplication on multi-socket servers. I am currently working with AMD India. This work was carried out when I was a student at the Indian Institute of Science. In cloud, often workloads run within virtual machines, and these virtual machines often host same or similar workloads using similar datasets. Many of the virtual machines also use similar OS images, libraries, etc. This leads to a lot of duplicate content. For example, in this picture we are showing two instances of MySQL Server, MySQL 0 and MySQL 1. They have many identical pages that are shown in purple color. The purpose of deduplication is to identify duplicate content and get rid of extra copies to save on memory. We do this by first scanning physical page frames. Once we find duplicated pages, we can retain one of the copies and share it across processes or VMs after marking it copy on write. If one of the applications start changing the content, copy on write allows us to provide the process its own private copy of the page. This support already exists in Linux and other software ecosystem. For example, in Linux it is called kernel same page merging or KSM. In VMware's ecosystem it is called transparent page sharing or TPS. In this work we focus on KSM. When we experimented on our Linux server with KVM the hypervisor with KSM turned on, we observed something interesting. The graph here shows some applications. Y-axis is the normalized runtime. For each application, we run two identical instances, that is instance 0 and instance 1, which are represented by two separate bars here. These are being run on two different VMs running on two different sockets. Instance 1 is launched just after instance 0. When KSM is turned off, we can see that the runtime of both the instances is roughly similar. But when KSM is turned on, one of the instance, very specifically the instance 1, becomes significantly slower. When we investigated the reason for the 20 to 46% slowdown of instance 1, we found an interesting interaction happening between the non-uniform memory architecture or NUMA-ness of the server and memory duplication. But before we get deeper into this, let's do a quick review of what NUMA is. In large servers, we typically have multiple sockets, where each socket has one processor and a set of local DRAM DIMM. Each of these processors can access the remote DRAM DIMM as well, but the access latencies or bandwidth depend on the distance between the CPU and the memory. For example, a remote memory access could be 50% slower than the local memory access. Clearly, the performance of an application depends on the data placement and how often it accesses remote memory. To validate the reason behind the slowdown of the instance 1, we measured what percentage of memory accesses are going to the local and remote memory. When KSM is turned off, it is easy to see that memory accesses are local for instance 0 as well as for instance 1. When KSM is turned on, instance 0 still behaves the same, but surprisingly, instance 1 sees a significant fraction of memory accesses going to the remote socket, which ultimately causes a significant drop in its performance. At this point, it is natural to ask, why is it that the instance 1 always slows down while there is no impact on instance 0? The answer lies on how KSM decides which of the page to retain and which copy to release. Surprisingly, the decision making is quite arbitrary today. In our experiments, we launch instance 0 and then instance 1. KSM keeps the page which is scanned later, which means that the order of scanning dictates page placement. The order of scanning depends on the order in which the processes were launched. In our case, KSM is always keeping the pages which are allocated by instance 0 and releasing the pages which are allocated by instance 1, as instance 1 was launched just after instance 0. Hence, for all the duplicated pages, it is the instance 1 that suffers due to remote memory accesses in our case. Next thing we explored is whether could we use process priorities to resolve this issue. What if we made instance 1 a high priority instance? We found that it doesn't help. We are showing this for one example application, which here is B-tree. Here x-axis shows time and y-axis shows the throughput of an application B-tree. Blue line is for the low priority process and orange line is for the high priority process. We can see that once KSM has removed duplicated content, the low priority instance is executing at a higher throughput. The reason for this is what we just discussed. The low priority instance was launched slightly before the high priority instance. So high priority process may suffer high remote memory accesses and there is no way to tune the system. Having made these interesting observations, our objective is to enhance KSM in Linux to contain performance variation and avoid priority subversion. We achieved these objectives with nuKSM or NUMA-aware KSM. We made two contributions. One, we were the first to show how memory deduplication and NUMA can conflict with each other. Second, we proposed a solution for that.
At a high level, the basic idea of the solution is very simple. What we want to do is, instead of looking at which instance ran first or later, what we try to do is which of the copies of duplicate content is getting accessed more often, which means they are probably likely to be accessed more often in future as well. In this example, let us assume that out of the purple pages which are duplicate content across two instances, red ones are the ones which are relatively frequently accessed. So what we do is we keep the frequently accessed ones where they are and release the other copies. What happens due to this is the overall overhead penalty of the remote memory accesses goes down. If you can keep frequently accessed pages, it would minimize the impact of remote memory accesses. But the challenge is how to identify such pages. If we try to add some mechanism, it will definitely add some overhead. Instead, we leverage the information that is already maintained by Linux. Linux maintains active list and inactive list to be able to swap pages under memory pressure. Active list contains more frequently accessed pages while inactive list contains infrequently accessed pages. When one copy of the page is in active list and another is in inactive list, we release the page which is in inactive list. This minimizes the aggregate impact of remote memory accesses. But in case when both of them are in active or inactive list of both the nodes, in those scenarios we follow a fair distribution of pages and not favor only one instance.
If both the pages identified as duplicate are in the active list or inactive list, then we follow a round robin algorithm on which page to retain. For example, here we could see that the pages with content C0, C1, C2 and C3 are in the active list for both the applications. nuKSM would try to evenly distribute the percentage of remote memory accesses and thus evenly distribute the penalty incurred by remote memory accesses. For example, if the algorithm decides to retain pages with content C0 and C2 on node 0, close to MySQL 0 and C1 and C3 on node 1 close to MySQL 1. So now for MySQL 0, accessing the page with content C1 and C3 will be remote memory accesses, and for MySQL 1, accessing the page with content C0 and C2 will be remote memory accesses. In this way, the penalty incurred for accessing remote memory is being evenly distributed across the instances. Now we'll see that how this policy helps our KSM. Before we do that, we can talk about our platform. We used a 2-socket Intel Skylake machine with 18 cores per socket. Each socket has 192 GB of memory available. We have used a bunch of workloads: CZ from the NAS parallel suite, Access Bench, MySQL, a popular database service, and also micro benchmarks like random access and B-tree lookups. So now we look at how we benefit out of nuKSM. We can see that in case of KSM, instance 0 and instance 1 had significant performance difference. But with nuKSM, this difference is now within the run-to-run variation. KSM introduces high performance variability and thus unfairness among applications running on different VMs. In contrast, the difference is almost negligible in nuKSM. Different instances of an application witness different amount of remote memory accesses under KSM. However, with nuKSM, we observe that the remote access percentages are almost equal across both the instances for every application. This confirms that nuKSM evenly distributes the local and remote memory accesses unlike KSM and helps avoid performance variability and unfairness in application performance. nuKSM has the ability that it suffers less NUMA overheads due to deduplication, but we also quantified fairness as per the formula shown here. The more it is close to 1, better fairness across application is identified. We could see that we provide much better fairness across instances in nuKSM. None of this is coming at the cost of memory saved. You can find more details about the observations on the paper. nuKSM enables the user to configure which process should enjoy more or less local or remote memory access based on their priorities. Instead of introducing a new priority scheme, nuKSM inherits Linux process priority, that is nice values. For each page that is considered for deduplication, we calculate new share of the page as per the following formula. The higher the value of new share, more likely the page is to be retained. We conduct our experiments on 5 different priority configuration. Config C 10:1 means that the relative priority of the VMs running instance 0 and instance 1 are in the ratio of 10:1.
While moving from left to right on these graphs, the priority of VM running instance 0 decreases and the priority of VM running instance 1 increases. We are showing the results here for two example applications. What we are trying to show here is that for these two applications that are chosen, we can see that there is performance variation with KSM and we cannot actually control it, which is based on which instance started first and which instance started later. In case of nuKSM, we could control the distribution of pages to be retained, which allowed us to control the relative runtime of the applications based on priority. While going from left to right on these graphs, from configuration C 10:1 to 1:1, we can see that the runtime difference between the two instances of the application decreases. And with C 1:1 configuration, we can get a fair environment for the instances.
Beyond this, we also introduce another optimization which has nothing to do with NUMA as such, but we observe that nuKSM doesn't scale to larger memory sizes. KSM maintains two red-black trees for detecting identical contents, namely stable and unstable tree. For each page, KSM performs a search in the stable tree and an unstable tree to get a suitable candidate for deduplication. Full page comparisons are being done on the search path to detect identical contents. What we see here is that these trees grows with increasing memory size and hence the search path will have more comparisons. These trees are basically the centralized data structures. We convert these centralized data structures into decentralized data structures, specifically the stable and unstable tree into stable and unstable forest. The index of the tree within the forest to search would now depend on the page contents checksum. Since two pages with identical content will have the same checksum, hence we now have successfully reduced the search space, thereby reducing the unnecessary number of comparisons. We can upper bound the cost of search by adjusting the number of trees so that we can have a limit in the number of levels we have for each tree to search on. So with increasing memory capacity of the machine, we can increase the number of trees to provide a limit in the number of comparisons to be done on each search. This example shows the benefits of decentralizing search operations. We show how this better scaling can avoid out-of-memory error due to faster deduplication that may happen in normal KSM. We run two instances of access bench and a background job that gradually increases memory pressure in the system because KSM takes longer to find and deduplicate identical pages. It runs out of memory because of the background job in about 15 minutes. nuKSM is faster and is able to run all workloads till completion. The second graph shows that when out of memory occurs in KSM, nuKSM had deduplicated more than 6 GB of memory. Overall, the experiment shows that nuKSM is more responsive than KSM. Now we'll come towards the key takeaways of nuKSM. Our observation was that KSM is NUMA-unaware. We observed arbitrary or uncontrolled performance variability across different instances of the same application under KSM. Subversion of priority goals was also observed. We observed that KSM is not much responsive with large memory. We proposed nuKSM, that is NUMA-aware KSM, which provided deterministic performance and fairness across different instances of the application. It was in line with the priority objective and it also provided enhanced responsiveness. Please refer to the paper for more details on how nuKSM scales beyond 2 VMs or processes and many more details. You can get the source code of nuKSM as a part of the artifact that is provided in the mentioned link.